Good evening, and welcome. Wherever you are right now, I'm glad you found your way here. Maybe you're lying in the dark with the lights turned low, or on a long train home watching the world blur past the window, or simply ready to let a long day go. However you arrived, there's nothing you need to do tonight except breathe slowly and let your thoughts grow soft. Before we begin though, I'd love to know one thing. Where in the world are you listening from tonight? People drift into these quiet corners from everywhere. A flat in a rainy city, a farmhouse far from any streetlight, a small room on the other side of the planet where it's already tomorrow. If you feel like it, leave a note below to say hello and where you are. There's something comforting about knowing that all across the world, in 100 different time zones, people are settling in under the same strange and beautiful sky. And if you find these slow explorations soothing, a gentle like and a quiet subscribe help more than you might think. Channels like this one are small, and they grow only when a few kind listeners decide to stay. Every like tells the machinery behind the scenes that this calm little corner is worth showing to someone else who can't sleep. And every subscription is a small vote that says, please keep making these. It costs you nothing. It takes a moment. And on this end, it means the world. So thank you, truly, whether you're here for the first time or the 50th. Now, one gentle note before we begin. Tonight's subject is quantum physics, which has a reputation for being difficult. Please don't let that worry you. I promise there will be no equations to solve, no formulas to memorize, and no test at the end. If anything, my goal is the opposite of a physics class. I want to make the strangest ideas in all of science feel gentle, almost like bedtime stories, so that you can follow along in a drowsy, half-dreaming sort of way. And if you happen to fall asleep somewhere in the middle, that's not a failure at all. That's exactly what this is for. Consider it the highest compliment you can give me. Here's what I find lovely about the quantum world. It sounds impossibly complicated, and yet at its heart, it's really just a handful of surprising rules about the very, very small. The things that make up you and your bed, and the light reaching your eyes, and the distant stars, all follow these rules. They've been following them quietly the whole time, long before anyone noticed. For most of human history, we simply couldn't see small enough to catch them in the act. So tonight, we're going to shrink. Not literally, of course, but in our imaginations. We'll travel down past the things we can touch, past dust and cells, down to atoms, and then down even further to the tiny flickering pieces inside them. And as we go, the ordinary rules of the world will start to loosen and bend in ways that once astonished the cleverest people alive. We'll meet particles that behave like waves, objects that seem to be in two places at once, and a kind of emptiness that isn't really empty at all. We'll take it slowly, one idea at a time, with plenty of gentle detours and familiar comparisons to hold on to. You don't need to hold all of it in your head. Let the ideas wash over you like the sound of rain. Some will stick, some will drift away, and both are perfectly fine. So find a comfortable position, let your shoulders drop, and let's begin our quiet journey into the hidden machinery of the universe. Our story begins, as many good stories do, with something ordinary that turned out to be a mystery in disguise. It begins with the simple glow of warm things. You've seen this 1,000 times without thinking about it. The coils of a toaster slowly blushing orange. The last embers of a campfire, deep red in the dark. A blacksmith's iron heated until it shines a fierce yellow white. As things get hotter, they glow, and the color of that glow changes in a very reliable way. Cooler things glow dull red, Hotter things move toward orange, then yellow, then a brilliant bluish-white. This pattern is so dependable that we barely question it. But at the end of the 1800s, it hid a problem that would crack the foundations of physics wide open. Back then, scientists were feeling rather pleased with themselves. The great laws of motion, of heat, of electricity and magnetism all seemed to be falling into place. Many believed that physics was nearly finished, with only a few small details left to tidy up. And one of those small details was this business of glowing objects. Surely, they thought, we can explain exactly how much light of each color a warm object should give off. It seemed like a tidy little calculation. But the tidy little calculation refused to behave. When physicists used the best theories of the time to predict the glow of a heated object, the math worked reasonably well for the warm, reddish colors. Then it went completely mad. It insisted that the object should also pour out an enormous, ever-increasing flood of energy at the bluer end, toward the ultraviolet and beyond. According to the equations, every warm thing in the universe, including your own gently glowing body, should be blasting out an infinite amount of high-color light. Which is, of course, nonsense. If it were true, sitting near a warm oven would be instantly lethal, and so would everything else. This absurd result even earned a dramatic nickname. People called it the ultraviolet catastrophe, not because anything actually exploded, but because the theory did. No matter how the equations were adjusted, the answer kept spiraling off into impossibility. Something at the very heart of the physics was simply wrong, and nobody could see what. Then, in the year 1900, a careful and rather conservative German physicist named Max Planck found a way through. Planck was not a rebel. He loved the established rules and had no wish to overturn them. But he was stuck, and out of something close to desperation, he tried an idea that felt almost like cheating. He asked a strange question. What if warm objects can't give off energy in just any amount at all? What if energy can only come out in tiny, fixed portions, like sand poured one grain at a time rather than as a smooth, continuous stream? To picture what he did, imagine two ways of turning up a light. One is a smooth, dimmer dial that can be set to absolutely any brightness you like, with no gaps in between. The other is a switch with a series of firm little clicks, so the brightness can only step up notch by notch, and nothing in between is allowed. For centuries, everyone had assumed that energy was like the smooth dial. Planck proposed that, at the smallest scale, it behaves more like the clicking switch. Energy comes in packets. He called these smallest packets quanta, from the Latin word for how much. When Planck put this odd little rule into his equations, the catastrophe simply vanished. The infinite flood of energy dried up, because at the high-color end, the required packets were too big and too expensive for a warm object to easily afford. The predictions suddenly matched reality perfectly, for every color and every temperature. It was as if a door that had been jammed for years swung open at the lightest touch. To describe the size of these energy packets, Planck needed a number, a sort of exchange rate between the color of light and the amount of energy in each packet. That number is now called Planck's constant, and it is astonishingly small. So small that in ordinary life, the steps between energy packets are far too fine for us to ever notice. The glow of your toaster looks perfectly smooth to your eye. The clicking, stepwise nature of energy only reveals itself when you look at the tiniest scales, which is exactly why it stayed hidden for so long. Here is the part I find quietly moving. Planck himself didn't really believe his own idea. He thought of it as a mathematical trick, a temporary patch to make the numbers come out right, and he assumed that someone cleverer would eventually explain the glow of warm things without any of this strange business of packets. He had no wish to start a revolution, and yet he had. That small, reluctant idea, buried in a modest paper, was the first crack in the smooth wall of classical physics. Through that crack, a whole new understanding of reality would slowly pour. But that first night, it was just a quiet fix for the puzzle of why warm things glow the way they do. Rest with that thought for a moment. The most enormous changes often begin not with a shout, but with a careful person reluctantly trying something new because nothing else would work. Planck had opened the door only a crack, and he rather hoped it would swing shut again. It did not. The next person to push it wider was a young Peyton Clark, who would become the most famous scientist who ever lived. To understand what he did, we need to talk about light, and about a small experiment that behaved very rudely toward the physics of its day. The experiment was this. If you shine light onto certain metals, the light can knock tiny particles called electrons right out of the metal surface. Electrons are the little bits of electric charge that flow through wires and make your devices work, and normally they're held snugly inside the metal. But light, it turns out, can shake some of them loose. This is called the photoelectric effect, and at first it seemed harmless enough. Now everyone at the time was quite sure that light was a wave, and they had good reason. Light bends around corners, spreads out, and ripples in exactly the way waves do. So they made a very reasonable prediction. If light is a wave, then a brighter light carries more energy, and a brighter light should therefore kick the electrons out harder and faster. Turn up the brightness, and the electrons should come flying out with more punch. Dim the light, and they should come out weakly. Simple. But nature had other plans, and the results were baffling. The brightness of the light barely mattered for how hard the electrons were kicked. What mattered was the color. Redder light, no matter how blindingly bright you made it, might not knock out a single electron. But bluer light, even when it was dim and faint, would pop electrons loose immediately. There was a sharp threshold tied entirely to the color, and below that threshold nothing happened at all, however much light you poured on. A wave shouldn't behave like that. A big enough wave should eventually do the job. This one simply wouldn't. Enter Albert Einstein in 1905, during a single miraculous year in which he published several ideas that each could have made a career. To explain the stubborn photoelectric effect, Einstein took Planck's reluctant little packets and did something Planck never dared to do. He said the packets were real. Light, Einstein proposed, isn't only a wave. It also arrives in tiny individual bundles of energy. We now call these bundles photons. And crucially, the amount of energy in each photon depends on the color of the light. Bluer light means higher energy photons. Redder light means lower energy photons. Suddenly, the whole puzzle made sense. Knocking an electron out of the metal is a one-on-one affair. A single photon strikes a single electron and hands over its energy. If that one photon carries enough energy, the electron is freed. If it doesn't, the electron stays put, no matter how many feeble photons come knocking afterward. Making the light brighter just means sending more photons. But if each one is too weak, a larger crowd of weaklings still can't do the job. Let me offer a gentle way to picture it. Imagine trying to break a window using rain. A soft mist, no matter how long it falls or how thick it gets, will never crack the glass. Each tiny droplet is simply too gentle. But a single heavy hailstone, arriving just once, can shatter the pain in an instant. Redder light is like the endless soft mist. Bluer light is like the hailstone. It isn't the total amount of water that matters. It's how much punch each individual arrival carries. The photoelectric effect was telling us that light, deep down, comes in individual arrivals, each with its own fixed amount of energy. This was a genuinely radical claim, and many physicists disliked it because the wave picture of light was so successful and so beloved. And here's the truly strange part. They were not wrong about the wave. Light really does behave like a wave in countless situations. Einstein wasn't throwing that away. He was saying something far stranger. Light is somehow both. It spreads and ripples like a wave, and it also arrives in little packets like particles, and which face it shows you depends on how you look at it. This idea came to be called wave-particle duality, and is one of the first deep shocks of the quantum world. Our ordinary language wants everything to be one clear thing. A thing is either a wave or a particle, we feel, not both. But light politely declines to obey our language. It was the universe's first hint that the neat categories we use to carve up reality are our inventions, not nature's, and that down at the smallest scales, those categories start to blur. Einstein received the Nobel Prize, by the way, largely for this explanation of the photoelectric effect, not for his more famous work on relativity. That's how important it turned out to be. What had looked like a small, rude little experiment became a cornerstone. And it left everyone with a haunting new question. If light, the most familiar thing in the world, can be both a wave and a particle, then what about everything else? Hold that gentle unease as we drift onward, because the answer is stranger still. If there is one experiment that captures the whole mystery of the quantum world in a single image, it's this next one. It's beautifully simple. You could almost sketch it on a napkin, and yet the greatest physicists of the last century have called it the deepest puzzle in all of science. It's known as the double-slit experiment, and I'd like to walk you through it slowly, because it rewards a patient mind. Picture a wall with two narrow, parallel slits cut into it side by side, like two thin doorways. Behind that wall, a little further back, is a screen that records wherever something lands. And in front of the wall, we have a source that fires things at the slits. Let's begin, as the early experimenters did with light. To understand what we see, first imagine sending waves at the two slits, like ripples on a pond, passing through two gaps in a barrier. Each gap becomes the source of a new set of ripples spreading outward, and these two sets of ripples overlap. In some places, the peak of one wave meets the peak of another, and they add together into something stronger. In other places, a peak meets a trough, and they cancel out into stillness. The result on the screen is a striped pattern. Bright band, dark band, bright band, dark band, fading out toward the edges. Physicists call this an interference pattern, and it is the unmistakable signature of waves. When light produces these stripes, as it does, it's behaving like a wave. So far, nothing troubling. Now here's where the ground begins to tilt. Modern equipment lets us turn the light source down so low that it releases just one photon at a time. A single tiny bundle of light, all alone, traveling toward the two slits. We already learned that light comes in these little packets, so surely each lone photon must go through one slit or the other, like a single pebble tossed through one of two doorways. And if it's just pebbles, one at a time, we'd expect them to pile up in two simple heaps on the screen, one behind each slit. No stripes, just two clumps. But that is not what happens. You send the photons through one by one, each landing as a single tiny dot, seemingly at random. A dot here, a dot there. No pattern at first, but as the dots accumulate, hour after hour, patient and slow, they gradually assemble themselves into the striped interference pattern, the very pattern that only waves are supposed to make. Somehow, each solitary photon, with no companions to overlap with, still lands as if it were part of a wave passing through both slits at once and interfering with itself. Sit with how odd that is. A single, indivisible packet of light, sent alone, behaves as though it explored both doorways at the same time, and then quietly folded that combined journey into where it finally chose to land. It's as if each photon travels not as a definite little thing on a single path, but as a spread-out cloud of possibilities that goes every which way, and only becomes a single dot at the last instant when it strikes the screen. Naturally, the early physicists thought, let's just watch. Let's put a little detector at the slits to see which one each photon actually goes through, and settle this ghostly business once and for all. And when they did exactly that, the strangest thing of all occurred. The moment they set up a detector that could tell which slit each photon passed through, the stripes vanished. The interference pattern disappeared, and instead the photons piled up in two simple clumps, exactly like ordinary pebbles. As soon as the universe was forced to give a clear answer about which path was taken, the wave-like spreading collapsed, and the photon behaved like a plain particle. Turn the watching device off, and the stripes come back. Turn it on, and they're gone again. It's not that clumsy equipment was bumping the photons around. The effect appears even with the most delicate, gentle detectors imaginable. The mere fact that the which path information exists somewhere, that it could in principle be known, is enough to erase the wave-like behavior. Being observed changes what happens. Not observed by a human necessarily, but observed in the sense that the information leaks out into the world. And before you dismiss this as some quirk of light, I should tell you that this experiment has been repeated with matter. Not just photons, but electrons. Then whole atoms. Then large molecules made of hundreds and even thousands of atoms. Elaborate structures far bigger than anything you'd normally imagine behaving like a wave. In the most extreme versions, done by patient teams in Vienna, molecules of thousands of atoms have been sent through and have still built up the telltale stripes, still behaving as though each one passed through in a spread-out wave-like way. The same eerie result appears every time. Left unwatched, these tiny things behave like waves of possibility. Watched, they snap into definite little particles. This gentle experiment, with its two thin slits and its patient dots, sits at the very center of the quantum mystery. It tells us that at the smallest scales, things do not travel along single, definite paths the way a thrown ball does. Instead, they move as spreading clouds of maybe, exploring every route at once until something forces them to commit. Only in the act of being measured does the cloud of possibilities pick a single outcome. What that really means, and why the universe should work this way, is a question we'll keep circling all night. For now, let it settle over you like a soft fog. The world, when no one is looking, is far less definite than it appears. By the 1920s, physicists had a growing pile of these unsettling clues, and they badly needed a proper language to describe them. The old rules that Isaac Newton had given us, the ones that predict exactly where a thrown ball will land, simply broke down in the world of the very small. Tiny things spread out like waves, refused to commit to a path, and only settled into a definite state when measured. Nobody had a clean way to write all of this down. Then, in 1926, a physicist named Erwin Schrödinger gave us one, and it quietly became the beating heart of quantum physics. Now don't worry, we're not going to look at the actual equation. It's a lovely thing to a mathematician, but for us tonight, it's enough to understand the beautiful idea underneath it. Schrödinger's insight was to describe each tiny object not by a single position, but by something called a wave function. The wave function is, in a sense, a complete description of everything that could happen to a particle. It's a spread-out cloud of possibilities that says, in effect, the particle is somewhat likely to be here, less likely to be there, quite unlikely to be way over there. It doesn't give one answer. It gives a whole landscape of chances. Think of a weather map, the kind that shows the chance of rain across a whole country. It doesn't tell you it will definitely rain on your street at 3 o'clock. It shows a smooth spread of probabilities, heavier here, lighter there, all at once. The wave function is a bit like that, but for where a tiny particle might be found. Wherever the cloud is thick, the particle is likely to turn up. Wherever the cloud is thin, it's unlikely. And the strange, wonderful thing is that until you actually check, the particle doesn't seem to have a single location at all. It genuinely exists as that whole spread of maybes. What Schrödinger's equation does is describe how this cloud of maybes flows and changes over time. And here's a detail I find lovely and calming. As long as nobody looks, the cloud evolves in a perfectly smooth, gentle, predictable way. It ripples and shifts like the surface of a still pond, disturbed by a breeze. There's nothing jumpy or random about it. The wildness, the uncertainty, only enters at one specific moment, and that moment is measurement. When you finally look, when you fire up a detector and demand to know where the particle is, the whole spread-out cloud suddenly gathers itself into a single definite answer. Here it is, right here. The soft fog of possibilities condenses, in an instant, into one sharp fact. This picture is profoundly different from the older clockwork view of the universe. In the old picture, every particle had a definite position and a definite motion at every moment, whether you looked or not, like planets tracing exact paths around the sun. In Schrödinger's picture, before you look, there is no single position, only the cloud of likelihoods. Reality, at the smallest scales, is not a set of definite little dots moving along tracks. It's a shifting sea of probability, and definiteness only crystallizes when the world is somehow questioned. It was Schrödinger's colleague, a physicist named Max Born, who worked out exactly how to read the cloud as probabilities, how the thickness of the fog in each place tells you the chance of finding the particle there. This probability reading is one of the most tested ideas in all of science. It has never once failed. Every glowing screen, every laser, every chip, in every device you own, ultimately runs on the mathematics of these clouds of maybes. And the equation succeeds in the most spectacular way when we point it at the atom, which is where we're headed next. But before we go, let me leave you with the strangeness at the center of it, because Schrödinger himself never made peace with it. He gave the world the equation that describes the cloud of possibilities, and then spent much of his later life deeply uneasy about what it implied. He disliked the idea that a particle has no definite location until it's observed. It felt, to him, like the universe was refusing to be pinned down, refusing to simply exist in a clear and honest way when no one was watching. He had built the most useful tool in quantum physics, and he wasn't sure he believed the picture it painted. There's something very human in that. Sometimes we create the very things that unsettle us most, and we spend the rest of our days trying to understand what we've made. Let us now do the thing we've been building toward, and drift down into an atom itself. Atoms are the small building blocks that make up everything you can touch. Every breath of air, every drop of water, every part of your own body is built from them, and they are unimaginably tiny. If you could line up atoms side by side, it would take millions of them just to span the width of a single human hair. And yet, inside each one is a little world, and it runs entirely on quantum rules. The old picture of the atom, the one you may have seen as a child, looks like a little solar system. A dense center, called the nucleus, sits in the middle like a sun, and tiny electrons whirl around it in neat circular orbits like planets. It's a charming image, and it's also wrong. That picture actually caused physicists a great deal of grief, because according to the older physics, an electron whirling around like that should constantly bleed away energy and spiral inward, crashing into the nucleus in a tiny fraction of a second. If that were true, no atom could exist for more than an instant, and neither could you. Clearly something was holding the electrons up. But what? The answer came from the cloud of maybes we just met. An electron in an atom is not a little planet on a track. It's a spread-out wave of probability, wrapped around the nucleus in a particular standing pattern. Imagine the gentle, unmoving shapes a vibrating drumhead or a plucked string can hold. Patterns that stay put and shimmer in place. The electron settles into shapes like that around the nucleus. We call these shapes orbitals, and they're better thought of as fuzzy clouds of presence than as paths. The electron isn't racing anywhere. It's simply spread around the nucleus as a soft, three-dimensional cloud, thicker in some places, thinner in others. And here is the first beautiful consequence. The electron can't just settle into any old shape. Only certain special patterns are allowed, in the same way that a guitar string can only ring at certain clear notes and not the muddy in-between pitches. Each allowed pattern comes with its own fixed amount of energy. So an electron in an atom can only have particular, specific energy levels, like a staircase with fixed steps and no ramp. It can sit on one step or another, but never hover in between. This staircase of energy levels explains something you see every single day, something genuinely lovely. When an electron drops from a higher step to a lower one, it releases the leftover energy as a single photon of light, with a color set precisely by the size of the drop. And when light shines on an atom, an electron can absorb a photon and jump up a step, but only if that photon carries exactly the right amount of energy for the jump. This means every kind of atom gives off and drinks in its own exact set of colors, as unique as a fingerprint. It's why a neon sign glows that particular warm red, why sodium streetlights are that distinctive amber, why fireworks bloom in the specific colors of the metals inside them. And most wonderful of all, it's how we know what the distant stars are made of. We can't visit them, but we can catch their light, spread it into its colors, and read the fingerprints of the elements written in the gaps. The whole recipe of the cosmos, revealed in bands of color, all because electrons can only stand on certain steps. There is a second consequence, though, and it runs even deeper. It is the reason you are not, right now, quietly sinking through whatever you are resting on. Every electron carries a subtle trait that physicists named spin. The word is a bit of a trap, because an electron is not truly twirling like a little top, yet the name has stuck. What actually matters is that spin comes in just two varieties, which we can gently call up and down. And electrons follow a strict, almost unsociable rule. First, written down by a physicist called Wolfgang Pauli. The rule is simple to say. Within a single atom, no two electrons are ever allowed to settle into exactly the same state at exactly the same moment. They will not share. Once one electron has taken a certain pattern and spin, that seat is closed, and every other electron must find its own. This principle, the exclusion principle, is one of the quiet giants holding the world together. Since electrons are barred from all crowding into the lowest, snuggest level, they are forced to climb, filling one rung, then the next, then the one above that. That climbing is the whole reason atoms have an inner architecture at all. It is why chemistry happens, why one element behaves unlike another, why they join in all the intricate ways that give us water and stone and breathing, growing things. Take away this single refusal to share, and every atom would sag into the same dull, collapsed lump, with no chemistry, no difference, and no us. And there is something you can feel with your own hand. Press your palm flat against the tabletop. The electrons in your skin and the electrons in the wood are forbidden from occupying the same states, so they push back rather than merge. That pushback, that quiet insistence of matter not to be crushed into itself, is a great part of why solid things feel solid, and why you rest on your chair instead of oozing through it. It is a curious idea to drift off on. The floor beneath you holds firm, not really because atoms are tiny hard pebbles, but because the faint clouds of electrons inside them will not, under any circumstances, overlap. Solidity, the plainest fact about the everyday world, turns out to be a soft quantum rule wearing a disguise, humming silently beneath everything your hands have ever known. We have now met the cloud of maybes more than once, this reluctance of very small things to hold a single settled state until the moment they are measured. In the 1920s, a young physicist named Werner Heisenberg found a way to put into words just how far that fuzziness reaches, and what he found is so arresting that it still makes people stop and think 100 years on. We call it the uncertainty principle, and it says something quietly humbling about the outer edge of what anyone can ever know. Here is the heart of it, in ordinary language. For a tiny particle, some pairs of facts can never both be known perfectly at the same instant. The most celebrated pair is position and motion. Position is simply where the particle sits. Motion is how it travels, its speed together with its direction. And the principle tells us that the sharper you fix where a particle is, the more hopelessly smeared its motion becomes, while the sharper you fix its motion, the more its location dissolves into a fog. One can be crisp or the other can be crisp, but never the two together. Nature quietly forbids it. In daily life, of course, this sounds absurd. A bicycle leaning against your wall has a perfectly clear position, and a perfectly clear speed as well, which is none at all. There is no trade-off to be seen. And that is quite true, for bicycles and teacups and anything of ordinary size. The blur exists for them too, but it is so vanishingly small that it changes nothing you could ever notice, not in 1,000 quiet lifetimes. Only far down, among electrons and atoms, does the trade grow wide enough to rule everything. The vital point, and the one most often misread, is that this has nothing to do with clumsy instruments. It is tempting to suppose that, of course, a tiny thing is hard to measure without nudging it. And there is a small truth hiding there. To glimpse a particle, you usually have to bounce something off it. A photon, perhaps. And that faint collision really does give it a shove. But Heisenberg's idea goes far beneath that. The blur is not merely a shortcoming of our tools. It is stitched into what a particle actually is. Even in some flawless, dreamlike measurement that disturbed nothing whatsoever, the trade-off would still be waiting there. A particle with a truly definite position simply does not carry a truly definite motion. It is not that the answer is hidden from us. It is that there is no sharp answer sitting there to be found. You can feel why, if you think back to the cloud of maybes. A particle is that spread out wave. If you squeeze the wave into a tight little spike, so that its position is very sharp and definite, the wave becomes choppy and jagged, and it turns out that a choppy wave contains a wild mixture of many different motions all jumbled together, so its motion is a blur. If instead you let the wave spread out into a long, smooth, gentle ripple, its motion becomes clean and well-defined, but now it's spread over so much space that its position is anyone's guess. A wave simply cannot be sharp in both ways at once. That's not a flaw. It's just what waves are like, and tiny things are waves. Let me offer a soft image. Think of an old photograph. If the camera captures a single crisp instant, you can see exactly where a running child is, frozen in place. But you have no idea how fast they're moving. If instead, the camera holds its shutter open for a moment, you get a lovely motion blur streak that tells you all about the movement. But now, you can't say precisely where the child is. Sharp on where, or sharp on how fast. But never both. The universe, at its smallest scale, is a bit like a camera that can never do both at once, no matter how fine its lens. This unavoidable blur is not just a curiosity. It's one of the reasons the world can exist at all. Remember our worry that electrons should spiral into the nucleus and destroy the atom. The uncertainty principle is what saves them. If an electron ever settled right onto the nucleus, its position would be pinned down to a tiny point, which would force its motion to become wildly, enormously energetic, and that violent motion would immediately fling it back out again. The electron can't fall in and stay, because being that confined is forbidden by the trade-off. So it hovers in its cloud, held aloft not by anything pushing on it, but by the sheer impossibility of being too precisely located. The stability of every atom in your body rests on this gentle refusal of nature to be perfectly certain. There's something almost consoling in all of this. So much of human effort goes into the hunger for certainty, for pinning things down, for knowing exactly. And here, at the root of reality, we find a firm and permanent limit. Some things cannot be perfectly known, not because we aren't clever enough, but because there's simply nothing sharper there to know. The blur is real, and it's built in, and far from being a problem, it's part of what holds the world together. Perhaps there's a quiet lesson in that, to carry gently into sleep. Not everything needs to be pinned down to be real. Sometimes the softness is the point. We come now to an idea so strange that it has become the very symbol of quantum weirdness, and yet, told slowly, it flows naturally from everything we've already seen. It's called superposition, which is just a long word for a simple, startling notion. A tiny thing can be in a blend of two states at once, genuinely both, until the moment it's measured. In the everyday world, things are always one way or another. A door is open or shut. A candle is lit or unlit. Your tea is here on the table, or it isn't. Whatever you're not currently looking at is still in some definite state, just hidden from you. If a coin is spinning inside a closed cup, you might not know whether it's heads or tails, but you feel certain it's really one of them, and you simply haven't peeked. That's ordinary hidden information. There's a fact to the matter, and you just don't happen to know it yet. Quantum things are not like that, and this is the heart of it. When a tiny particle is in superposition, it is not secretly in one state while you remain ignorant. It is truly in a blend of both, at the same time, in a way that has real, measurable consequences. An electron spin can be genuinely up and down together. A particle can be genuinely on this side and that side together. It hasn't chosen. There is no hidden fact waiting to be uncovered. The bothness is the reality, right up until something forces a choice. We actually met this already, back at the two slits, though we didn't give it a name. Each lone photon went through both doorways at once, in a blend of the two paths, and that blend is exactly a superposition. The interference stripes were the fingerprint of the two possibilities overlapping and combining, which they could only do because both were genuinely present. If the photon had secretly gone through just one slit all along, there would be nothing to interfere with, and no stripes. The stripes STScI are proof that the bothness was real. Here's a gentle way to hold it. Picture a coin spinning so fast on a table that it becomes a shimmering blur, and while it spins, it's meaningless to call it heads or tails. It isn't secretly one of them under the blur. In its spinning, it's a genuine mixture of both, and only when it topples and settles does it become one clear face. A quantum superposition is a little like that endless spin. The tiny thing hovers in its blend, neither and both, until the world reaches in and makes it settle. The difference is that for a quantum particle, this isn't just our ignorance of a fast-spinning coin. It's a real physical in-betweenness that leaves fingerprints we can measure. It was Erwin Schrödinger himself, the very man who gave us the cloud of maybes, who came up with the most famous way of talking about this. And he did it not to celebrate the idea, but to poke fun at it, because he found it absurd. He imagined a thought experiment, purely in the mind, never actually performed. Picture a sealed box, he said, and inside it, a cat, along with a small device rigged to a single radioactive atom. Radioactive atoms are governed by quantum rules, so whether the atom has broken apart or not is, before you look, a superposition of both, broken and unbroken at once. And Schrödinger wired the box so that if the atom breaks, the cat is harmed, and if it doesn't, the cat is fine. So if the atom is truly in a blend of both states, then the whole box, cat included, should be in a blend too. The cat, absurdly, would be both alive and not alive at the same time, until someone opens the box and looks. Schrödinger's whole point was that this is ridiculous. Cats are large, warm, everyday things, and no one has ever seen a cat in such a blurry condition. He was trying to show that something must limit this strange bothness to the world of the very small, that surely it can't scale up to cats and boxes. And he was right to be puzzled. The puzzle of where the quantum weirdness stops and the ordinary world begins is one we still wrestle with. The best answer we have today has a name. It's called decoherence, and it's actually rather soothing. A single particle, kept perfectly isolated, can hold its delicate superposition. But the moment it touches the wider world and gets jostled by countless surrounding air molecules, stray light, and warmth, its neat bothness gets hopelessly tangled up with all of that surrounding chaos. And it very quickly loses the ability to show its blended wave-like behavior. It effectively settles into looking like one ordinary state or the other, extremely fast. A cat is made of an astronomical number of particles, constantly bathed in warmth and light and air, so any superposition would unravel almost instantly, far faster than any eye could catch. That's why we never see blurry cats. The largeness and warmth of everyday things protects them from the strangeness. Superposition is real, but it's shy. It survives only in the smallest, quietest, most carefully guarded corners. And in those corners, as we'll see, it turns out to be not just a curiosity, but a source of astonishing power. Some quantum effects are subtle. This next one feels almost like a magic trick, and yet it is happening, constantly, everywhere, including inside the star that warms your days and inside the very device you might be listening on right now. It's called quantum tunneling, and once you understand it, you'll never look at a solid barrier quite the same way. Start with the ordinary world. If you gently roll a ball toward a hill, and the ball doesn't have enough energy to reach the top, it rolls partway up, slows, stops, and rolls back down. It simply cannot get to the other side. It lacks the oomph. This is common sense, and in the large world, it's completely reliable. A barrier you don't have the energy to cross is a barrier you don't cross. Full stop. But a tiny particle is not a ball. It's a spread out cloud of maybes, that soft wave of possibility we keep returning to. And when this wave meets a barrier, something remarkable happens. The wave doesn't just stop dead at the wall. It seeps into the barrier and fades, gradually, like a sound growing muffled as it passes through it. If the barrier is thin enough, the faint remainder of the wave can leak all the way through to the far side. And where the wave reaches, there is some small chance of finding the particle, which means that every so often, a particle that classically should have been trapped simply appears on the other side of a wall it never had the energy to climb. It didn't smash through or go over. It was, in a sense, always faintly present on both sides, and sometimes it turns up on the far one. Let me offer an image to rest on. Imagine two quiet rooms separated by a thin wall, and someone speaking softly in one of them. You're in the other room, and mostly you hear nothing. But now and then, if the wall is thin, a faint word slips through, muffled but real. The sound didn't break the wall. It bled through it. Quantum tunneling is a little like that, but instead of sound, it's the particle's own presence that quietly bleeds across. The thicker the wall, the rarer the crossing, but it never quite drops to zero. This is not some laboratory curiosity that only matters to specialists. Quantum tunneling is one of the reasons the stars shine, and therefore one of the reasons you're alive. Deep in the heart of our sun, small particles are being crushed together to release energy in the process we call fusion. But these particles carry the same kind of electric charge, and like charges push each other away fiercely the closer they get. Even in the sun's tremendous heat and pressure, the particles don't actually have enough energy to shove all the way past that repulsion and touch. By the strict rules of the old physics, the sun shouldn't be able to burn the way it does. And yet it burns. It burns because every so often, two particles tunnel through the barrier of repulsion between them, slipping to the other side and fusing when they had no classical right to. The sunlight falling on your world, the warmth that makes life possible, pours out of a countless number of these tiny impossible crossings happening every second in the star's core. Take a slow breath and let that settle. You are warmed, quite literally, by particles cheating their way through walls. Tunneling also explains a certain kind of radioactivity, where unstable atoms slowly release particles that, by rights, should be locked inside them forever. The trapped particle's wave leaks past the barrier holding it, and over time, with a tiny chance on each attempt, it eventually escapes. This same patient leaking is what makes certain materials gradually and predictably decay, which, among other things, is how we date ancient rocks and old bones and measure the age of the Earth itself. And it lives in your technology too. There's a beautiful instrument called the scanning tunneling microscope that can actually make pictures of individual atoms, one by one, laid out like cobblestones. It works by holding an incredibly sharp needle, just a whisker above a surface, close enough that electrons tunnel across the tiny gap between the surface and the tip. By measuring that faint tunneling trickle as the needle glides along, the machine builds up a map so fine it reveals the atoms themselves. Its inventors were honored with a Nobel Prize, and it gave humanity its first direct glimpse of the atomic landscape. Tunneling also lives inside the memory chips in phones, cameras, and thumb drives, which store your photos and messages by deliberately coaxing electrons to tunnel across thin barriers. Every time you save a picture, you're quietly putting quantum tunneling to work. So the lesson of tunneling is a soft and strange one. In our world, we think of walls as absolute, here and not there, allowed and forbidden. But at the smallest scale, barriers are not perfectly solid. They're more like heavy curtains than stone. A particle, being a cloud of possibility rather than a hard little pebble, is never entirely on one side of anything. There's always the faintest whisper of it reaching beyond, ready, now and then, to slip through. It's a gentle reminder that the sharp edges we imagine in the world are, deep down, softer and more forgiving than they seem. We turn now to what may be the most beautiful and baffling idea in all of quantum physics, one that troubled even Einstein until the end of his life. It's called entanglement, and it describes a strange kind of connection between particles, a link that seems at first glance to defy the whole idea of distance. Let me build it carefully, because it's easy to describe it badly. Suppose you have two particles that are created together or interact in a certain way so that their fates become linked. Once linked, we say they're entangled. Now separate them. Send one to the far side of a city or a country, or even up into space and back down to a distant station. The entanglement remains. And here's the heart of it. If you now measure some property of one particle, say which way its spin points, you instantly learn something certain about the other particle, no matter how far away it is. If one comes up as spin up, the other will be found spin down, reliably, every time, the instant either is checked. Now, you might think, well, that's not so strange. Suppose I take one black ball and one white ball, and without looking, I seal each into its own box, then mail one box to the far side of the world and keep the other. When I finally open my box and find the white ball, I instantly know the far box holds the black one. No magic there. The two colors were fixed from the moment I sealed the boxes, and opening mine just revealed which had gone where. And for a long while, that's exactly what Einstein and many others assumed was really going on with entangled particles. They must, Einstein insisted, carry hidden little settings, decided at the moment they parted, quietly telling each one how to answer when measured. Nothing spooky, just information packed in from the start, like the sealed up balls. But entanglement is not like those two balls, and this is the astonishing part. The particles do not carry their answers with them from the start. Before measurement, neither particle has a definite spin at all. Each is in that blend, that superposition of both possibilities undecided. And yet, the instant one is measured and settles on an answer, the other settles into the perfectly matching answer, immediately, even though it too had no definite state a moment before. It's not that they were secretly coordinated in advance. It's that they were sharing a single undecided state stretched across the distance, and the choice, when it happens for both at once. To feel the difference, imagine two dancers, one in Paris and one in Tokyo, who have never agreed on a routine and are not in any contact. Yet the moment the Paris dancer, on a whim, chooses to raise her left arm, the Tokyo dancer raises his right arm in the same instant, as a perfect mirror. Not because either decided beforehand, not because a message flashed between them, but as though they had been, all along, two halves of a single dance that only chose its shape at the moment of the first movement. That's closer to entanglement than the seal balls, because with entanglement, the step truly isn't picked until one of them moves, and yet the matching is flawless across any distance. For decades, this was just a philosophical argument. Einstein was sure the particles carried hidden settings, the pre-settled picture, and that quantum theory was simply incomplete. Others suspected there really was some deeper, spookier connection. It seemed like the kind of dispute that could never be settled by experiment, only debated. Then, in the 1960s, a quiet Irish physicist named John Bell found something extraordinary. He worked out a clever way to tell the two pictures apart. He showed that if the particles really did carry hidden settings decided in advance, like colors sealed into boxes, then the results of many careful measurements would have to stay within a certain limit. But if quantum theory was right, and there were no hidden settings, the results would break past that limit in a specific, measurable way. Suddenly, the argument was no longer just philosophy. It was a test you could actually run. And run it they did, over many years, with ever greater care, closing every loophole and objection one by one. Physicists made pairs of entangled particles, separated them, measured them in carefully varied ways, and tallied the results. The verdict came in again and again, always the same. The hidden settings picture is wrong. The pre-settled picture is wrong. The particles really do not carry their answers in advance. Nature really is entangled in this deep and spooky way, exactly as quantum theory predicted, and exactly as Einstein hoped it wouldn't be. In 2022, the scientists who pioneered these beautiful experiments were awarded the Nobel Prize for finally settling it. Now at this point, a very reasonable excitement arises. If measuring one particle instantly affects its distant partner, could we use this to send messages faster than light, across the galaxy in an instant? And the gentle, firm answer is no. Here's why. When you measure your particle, the outcome you get is completely random. You can't choose it. You can't force your particle to come up a particular way in order to send a signal. All you and a distant friend would each see is your own string of random results. Only later, when you compare notes through some ordinary channel, no faster than light, would you discover that your random results were perfectly matched. The connection is real, but it carries no controllable message. Nature allows the spooky link, but closes the door on using it to break the cosmic speed limit. It's a remarkable balance, as if the universe permits this deep togetherness, precisely because it can never be exploited to send a signal. What entanglement truly means, at the deepest level, is still debated by thoughtful people. Some see it as a sign that separateness itself is not as fundamental as it seems, that two far apart particles can genuinely be parts of one indivisible whole. There are even bold thinkers who suspect that the very fabric of space, the way distances hang together at all, might somehow be woven out of countless tiny entanglements. That speculation at the frontier, unproven and wonderful. But the plain fact, tested beyond doubt, is strange enough on its own. In the quiet depths of the world, things that seem entirely separate can be joined in a way that pays no attention to distance. Somewhere out there, particles that once touched are still, in a sense, holding hands across the dark. We've now gathered a whole collection of strange facts. Tiny things spread out as clouds of maybes. They hover in blends of possibilities. They settle into definite states only when measured. Distant particles share undecided fates. All of this is thoroughly tested and beyond serious doubt. And yet, underneath all of it, sits a question we've been circling all night without quite landing on. What is actually happening? What is really going on in the world when nobody is looking? And what does it truly mean to measure something? This is often called the measurement problem, and I want to be honest with you. More than 100 years on, the brightest minds still don't agree on the answer. Tonight, we'll gently visit the main ways people have tried to make sense of it. The oldest and most widely taught view came from the great Danish physicist Niels Bohr and his circle, and it's usually called the Copenhagen interpretation, after the city where Bohr worked. Its attitude is almost stern in its restraint. It says, roughly, don't ask what the particle is doing before you measure it, because that question has no meaningful answer. The cloud of maybes is simply the best description there is. There's no hidden, definite reality underneath, waiting to be uncovered. When you measure, the cloud settles into a result, and that's all we can or should say. Reality, in this view, isn't quite definite until it's questioned, and asking for more is asking for something that isn't there. Many working physicists adopt a practical version of this and get on with their calculations, which produce flawless predictions. There's even an affectionate phrase for this attitude: shut up and calculate. The math works perfectly, so why agonize over what it means? But of course people do agonize because it's hard not to. If reality isn't definite until it's measured, then what counts as a measurement? Does it need a person? Surely not, most would say, since the universe managed for billions of years before there were any people to look. Does it need a machine, or just any interaction with the wider world? Where exactly is the line between the shadowy quantum world of maybes and the solid everyday world of definite things? The Copenhagen view tends to answer these questions with a shrug, and for many, that shrug is deeply unsatisfying. So others have offered bolder pictures. The most mind-stretching is called the many worlds interpretation, proposed by a young physicist named Hugh Everett in the 1950s. Everett took a radical step. He suggested that the cloud of maybes never actually settles at all. There is no collapse, no single outcome chosen. Instead, every possible outcome really happens, each in its own separate branch of reality. When you measure a particle that was in a blend of two states, the universe simply splits. In one branch, you see the first result. In another equally real branch, a version of you sees the second. Both are real, both continue. You only ever feel yourself in one of them, because the other you has quietly gone off into a world of its own. I know how that sounds, like the wildest science fiction, but its appeal to physicists is surprising. It requires no mysterious extra step where the cloud collapses. It just takes the smooth mathematics we already trust and refuses to add anything. The cost, of course, is staggering. It asks us to accept an unimaginable, ever-branching forest of realities, splitting at every quantum event, forever. Some find that elegant. Others find it extravagant beyond belief. Picture a great river that never merges but only braids, endlessly splitting into more and more channels, each flowing on, none ever rejoining. That's the shape of reality that many worlds ask us to imagine. There are other views still. In one, called the pilot wave picture, particles really do have definite positions all along, and they're guided through space by a real physical wave that pushes them around, a bit like corks carried on a hidden tide. It restores a kind of definite reality, but it pays for it by requiring that everything be subtly connected across any distance in a way that some find troubling. In another family of ideas, the cloud of maybes really does collapse, but it does so all on its own, spontaneously, as a genuine physical event that happens rarely for a single particle, but almost instantly for large clumps of them. That would make collapse a real thing nature does, not just something tied to our looking. And cleverly, it predicts tiny differences that experiments are slowly trying to test. And weaving through all of these is that soothing idea we met earlier, decoherence, which explains beautifully how the fragile blends of the small world get scrambled by contact with the wider world and come to look ordinary and definite to us. Decoherence tells us why we never see blurry cats. But, and this is important, it doesn't by itself tell us why we end up seeing one particular outcome rather than another. It explains the appearance of settling without fully explaining the choosing. So even our best tool leaves the deepest question open. Here's what I'd like you to take away, gently, as you rest. All of these interpretations make exactly the same predictions for every experiment we can currently perform. That's why we can't yet tell which, if any, is right. They agree completely on what you'll see in the lab, and disagree entirely on what it means. So the mathematics of quantum physics is the most precisely tested description of nature we have ever created. And at the same time, we genuinely do not know what it's telling us about the deep nature of reality. Isn't that a wonderful thing to sit with? We have a perfect map and no certainty about the territory. There's no shame in the mystery. It's simply the honest edge of human understanding. And there's a strange peace in admitting that some of the biggest questions are still, quietly, open. Let's turn now to something that sounds like it should be the simplest topic of all, and turns out to be one of the most surprising. Let's talk about nothing, about empty space itself. Because in the quantum world, nothing is never quite as empty as it seems. When we imagine truly empty space, we picture a perfect void. Take a seal box, remove every speck of matter, every mote of dust, every particle of air, cool it to the coldest possible temperature, shut out all light. Surely what's left is pure, silent nothingness. A stage with no actors, completely still. It's a very natural picture, and according to quantum physics, it's wrong. That perfectly emptied box is not still at all. It quietly seethes with activity. The reason traces back to our old friend, the uncertainty principle, the unavoidable blur. It turns out that the blur applies not only to a particle's position and motion, but also to energy over short stretches of time. Over a very brief instant, the energy in a patch of space cannot be pinned down to exactly zero. It's forced to flicker and fluctuate, just as a particle's position must remain a little fuzzy. And these flickers of energy are enough to allow tiny particles to briefly bubble into being and then vanish again, borrowing a little existence from the fluctuation and paying it back almost instantly. Physicists call them virtual particles. They wink in and out of the void so quickly that you can never catch one directly. But they're not merely imaginary. Empty space is, in a sense, gently boiling with them, a constant fizz of fleeting somethings appearing and disappearing everywhere, all the time. Now, I wouldn't ask you to simply believe such a strange claim on faith, and neither did physicists. The wonderful thing is that this invisible fizzing has been caught having real, measurable effects. The most elegant example is called the Casimir effect. Imagine placing two flat metal plates extremely close together, facing each other, in the emptiest space you can make. The constant fizz of virtual activity fills the space all around. But here's the subtle part. In the narrow gap between the plates, only certain sizes of fluctuation fit neatly, while outside the plates, fluctuations of every size are free to crowd in. This means there's slightly more of this restless energy pressing in from the outside than pushing out from the thin gap between. The result is a tiny but genuine force nudging the two plates together, pushed by nothing but the imbalance in the churning of empty space. It sounds like a fairy tale, but it has been measured carefully in real laboratories, first convincingly in the late 1990s, and it comes out just as the theory predicts. The emptiness really does push on things. Nothing has a texture after all. This restless energy of empty space also leads to one of the greatest unsolved puzzles in all of physics. And I'll share it with you because it's such a humbling story. We know the universe is not only expanding, but that its expansion is speeding up, driven by some mysterious push spread throughout all of space. Physicists call this dark energy, and it's natural to wonder whether the energy of the quantum vacuum, that fizzing of empty space, might be the source of it. The trouble is the arithmetic. When physicists try to calculate how much energy the churning vacuum should contain, they get a number vastly, absurdly larger than what the universe actually shows, not a little off. Off by a factor so enormous, it's hard to even say aloud. A 1 followed by roughly 120 zeros. It has been called the worst prediction in the history of physics. A spectacular mismatch between our best theory of the small and our observations of the large. Nobody knows how to resolve it. It sits there, a giant question mark, a reminder that for all our success, something deep is still missing from the picture. Even so, the fizzing vacuum is woven into the everyday workings of nature in ways we've confirmed with breathtaking precision. The constant swarm of virtual activity subtly nudges the energy levels of electrons in atoms, shifting them by the faintest amount. And when physicists measure that shift, it matches the calculation to many decimal places. The invisible churn is real, and its fingerprints are all over the world we can measure. So here is a thought to carry into the quiet. The emptiest space, the deepest void, the silence between the stars, is not truly empty and not truly silent. It hums, it fizzes, it's a restless humming stage, even when every actor has left. What we call nothing is really a soft, ceaseless activity, too fine and too fast for us to feel. Even in the greatest stillness, The universe is never entirely at rest. There's something oddly comforting in that, as you lie there in the dark. The quiet around you is alive. We're deep in the small world now, and I want to share the picture that many physicists consider the most fundamental of all, the deepest layer we've been able to reach. It's a shift in how to think about what everything is truly made of, and it's strangely beautiful. The idea is that, at the very bottom, the universe is not made of tiny things at all. It's made of fields, and everything is ripples. Let me build up to it gently. You already have a feel for a field, even if the word sounds technical. Hold two magnets near each other, and you feel an invisible push or pull across the empty gap. That influence, filling the space around the magnets, is a field. It has some strength and direction at every point in space. The space around the Earth has a field too, the one that gives things weight. A field, in the end, is just some quality spread out through space, having a value everywhere, like an invisible, all-filling mist. Now here's the great leap that quantum physics invites us to take. It says that these fields are the truly fundamental things, and that what we call particles are simply ripples in them. Picture a still pond stretching everywhere, in every direction, filling all of space. Give the pond a little poke, and a small ripple springs up and travels along. That traveling ripple, that concentrated disturbance in the pond, is what we experience as a particle. According to this view, there is an electron pond, a vast field filling the whole universe, and every electron that exists, including the ones in your body, is just a little ripple traveling in that one shared field. There is a light pond too, filling all of space, and every photon, every bit of light reaching your eyes, is a ripple in it. Each kind of particle is a ripple in its own kind of field. This reframes the whole world in a lovely way. When two particles collide in a great experiment, and new particles burst into being that weren't there before, it's no longer mysterious. You've simply splashed one field hard enough to raise fresh ripples in others. When a particle appears or vanishes, a ripple has formed or faded. The particles aren't little permanent marbles that get shuffled around. They're patterns, temporary shapes the fields hold for a while, the way a wave is a shape the sea holds and then lets go. The field is what's real and enduring. The particle is just the field briefly getting excited in one spot. And the forces of nature fit into this picture too, elegantly. When two particles push or pull on each other, we can understand it as them tossing ripples back and forth between them. Little disturbances passing through the shared fields, nudging each other along. Even the pull of magnets at bottom is a quiet exchange of these tiny ripples of light. It's a strange and graceful thought. The solid-seeming world of things bumping into things dissolves, at the deepest level, into a set of overlapping fields, endlessly rippling and exchanging ripples, like a vast orchestra where each instrument is a field and every particle is a single note being played. This field picture also gives us the closest thing we have to a complete list of nature's basic ingredients, a sort of grand recipe that physicists call the Standard Model. It's the roster of all the fundamental fields and their ripples, the particles that can't be broken down into anything smaller. There are the particles that make up ordinary matter, like the electrons in your body, and the smaller pieces, called quarks, that huddle together to form the cores of atoms. There are the particles that carry the forces, the ripples exchanged to make things push and pull, including the photon that carries light and electricity, and others that hold the hearts of atoms together, or drive certain kinds of radioactivity. And there are some wonderfully shy particles called neutrinos, so faint and so reluctant to interact that trillions of them are streaming through your body every second, straight through you and the whole Earth, as though none of it were there. One more piece deserves a mention, because it completed the picture only recently, and it explains something wonderfully basic. Why do some particles have weight, a heaviness, while others, like light, have none? The answer involves yet another field, one proposed in the 1960s and thought to fill all of space. As particles move through this field, some feel a kind of drag from it, and that resistance is what we experience as their mass, their heaviness. The more strongly a particle feels this field, the heavier it is. For decades, it was only a beautiful guess. Then, in 2012, in an enormous machine beneath the border of France and Switzerland, physicists finally stirred that field hard enough to raise a ripple in it, the particle we now call the Higgs, and confirmed it was really there. It was one of the great triumphs of modern science, the last major piece of the standard model clicking into place. The picture is magnificent, and it's also, we know, incomplete. It leaves out gravity, the force that holds you to the Earth and swings the planets around the Sun. Gravity has stubbornly refused to fit neatly into this quantum language of fields and ripples, and joining the two remains one of the great unfinished quests of physics. But even unfinished, the view it gives us is worth resting in. You are not, at the deepest level, a collection of tiny solid balls. You are a vast and intricate pattern of ripples in a set of invisible fields that fill all of space. A standing melody the universe is playing, for now, in the shape of you. So far, our journey has stayed mostly in the realm of physics, of particles and fields and empty space. But I'd like to gently bring things closer to home, closer to warmth and breath and living things. Because there's a young and fascinating field of science asking whether the strange quantum rules we've been exploring might also be quietly at work inside living creatures. It's called quantum biology, and I want to share it with you carefully, honestly marking where the ground is solid and where it's still shifting, because that honesty is part of the wonder. Consider first the way plants and other green things capture sunlight, the process at the base of nearly all life on Earth. When a bit of sunlight is caught by a leaf, its energy has to travel through a little forest of molecules to reach the place where it can be put to work, and it does this with remarkable efficiency, losing very little along the way. Some years ago, experiments hinted at something startling. It looked as though the captured energy might not simply stumble along one path at a time, but instead spread out and feel its way along many possible routes at once, in a wave-like quantum manner, as if quietly sampling every path to find the best one. This caused great excitement and headlines about plants being tiny quantum computers. Now here's where I want to be honest with you, because the story grew more subtle. As scientists looked closer and argued it through, many came to believe that the delicate wave-like effects don't actually last long enough in the warm and jostling environment of a living leaf to do the clever route finding that was first imagined. A good deal of what looked like deep quantum behavior appears to have a more ordinary explanation. The current, careful view is somewhere gentle in the middle. Quantum effects are certainly present in how light-harvesting molecules work, as they are in all chemistry. But the bold, early picture of a leaf performing quantum computations was probably overstated. It's a lovely example of science correcting itself, patiently trading an exciting story for a truer one. And the truer one is still quite beautiful. The second example is, to me, one of the most enchanting ideas in all of biology. Many birds migrate enormous distances, thousands of miles, and find their way with astonishing accuracy, in part by sensing the Earth's magnetic field. The question is how a living creature could possibly feel something as faint as the planet's magnetism. And the leading idea, still a hypothesis but a serious and actively studied one, reaches straight into the quantum world. It suggests that when light strikes a special molecule in a bird's eye, it creates a pair of particles whose quantum states are linked, a delicate arrangement sensitive to magnetic fields. The Earth's field would gently tip the balance of how these linked states behave, and that tiny quantum effect could subtly change what the bird sees, perhaps painting a faint impression of the magnetic landscape right onto its vision. Imagine that. A bird that may quite literally see the invisible lines of the Earth's magnetism, guided home each year by a quantum compass in its own eyes. Researchers are still testing whether this is truly how it works, but the evidence has been building, and it's a wondrous possibility to hold. The third example is quieter but firmer, and it happens inside you right now. Your body runs on countless chemical reactions, sped along by molecular helpers called enzymes. And in some of these reactions, a tiny particle needs to get from one place to another across a small barrier, the kind of barrier that, by the old rules, it shouldn't easily cross. Yet it crosses anyway, and the best explanation is our friend from earlier, quantum tunneling. The little particle slips through the barrier rather than climbing over it, exactly as particles do in the heart of the sun. Only here it's happening gently, at body temperature, inside the machinery of your own cells, helping to keep you alive. This kind of tunneling in living chemistry is fairly well established, a quiet quantum effect woven into the ordinary business of being alive. So what should we make of all this? I'd invite you to hold it lightly and warmly. Quantum biology is a young field, full of genuine excitement and also full of honest debate, where some claims are solid and others are still being tested and trimmed. What's clear is that the strange rules of the very small are not sealed away in cold laboratories and distant stars. They reach, at least sometimes, into the warm and living world, into leaves turning toward the light, into birds crossing continents, into the soft chemistry of your own breathing body. The line between the quantum and the living may be thinner than anyone once supposed. And there's something deeply peaceful in that thought as you lie here tonight. The same delicate rules that govern the dust of distant galaxies are, in their quiet way, also part of what it means to be alive. After a night spent among such strange and dreamlike ideas, you might imagine that quantum physics is a purely abstract thing, beautiful but useless, floating far above ordinary life. I'd like to end our exploration by gently correcting that, because the truth is the opposite. The strange rules we've been drifting through are not distant curiosities. They're already running much of the world you live in, quietly, all around you, every single day. You've very likely been holding quantum technology in your hands without ever knowing it. Begin with the device you might be listening on right now. At its heart are billions of tiny switches called transistors, the fundamental building blocks of every computer, phone, and screen on Earth. And transistors work because of the quantum behavior of electrons inside certain materials, the way those materials sit right on the boundary between letting electricity flow and holding it back. Understanding and controlling that behavior required exactly the quantum rules we've explored, the way electrons occupy their allowed energy levels and shuffle between them. Without quantum physics, there would be no transistors, and without transistors, no computers, no internet, no glowing screen, none of the modern world. The entire digital age rests, quietly, on this foundation. Then there's light itself, tamed. The laser, that perfectly pure focused beam, works by coaxing a great many atoms to release their light in exact, matched step, all at once, using the very rules of energy levels and photons we met inside the atom. Lasers read the music and movies off discs, carry vast rivers of information through glass fibers beneath the oceans, scan the items at every checkout, and perform delicate surgeries. Their cousins, the little glowing chips called light-emitting diodes, light your screens and your rooms, sipping only a trickle of power, again by letting electrons drop between quantum energy levels and give off their light. Every gentle glow of modern lighting is quantum physics at work. Quantum rules also let us see inside the human body without a single cut. In the hospital scanner that produces those remarkable images of soft tissue and the brain, the trick relies on a subtle quantum property of the cores of atoms inside you, a tiny magnetic character they carry, which can be nudged with magnetic fields and radio waves and made to reveal a detailed picture from within. It has spared countless people from exploratory surgery, and it runs on the same deep principles we've spent the night with. Even something as everyday as finding your way with a map on your phone leans on the quantum world. The satellites that let your device know exactly where you are keep time using atomic clocks, timekeepers so precise they rely on the exact, unchanging rhythm of energy jumps inside atoms, the very steps of that staircase we discussed. These clocks are so accurate they would lose or gain less than a second over many millions of years. Without their quantum precision, the whole system of knowing your location would drift and fail within minutes. Every time you follow a route, atoms are keeping time for you overhead, and we're only at the beginning. The strangest ideas of all, the ones we might least expect to be useful, are now being turned into a new generation of tools. Remember superposition, the ability of a tiny thing to be in a blend of states at once. Engineers are using it to build a wholly new kind of machine, the quantum computer, which stores information, not as plain zeros and ones, but as delicate blends of both, and harnesses entanglement, that spooky link, to weave those pieces together. For certain very hard problems, such machines could one day explore a vast landscape of possibilities all at once, in ways an ordinary computer never could. They're still young and fragile, these machines, because as we learned, superposition is easily spoiled by contact with the warm and noisy world, so they must be kept exquisitely cold and still. But they're real, and they're growing. Entanglement, too, is being put to work in a new kind of secret keeping. Because you cannot measure a quantum particle without disturbing it, two people can share a secret key encoded in entangled particles and know for certain whether anyone has tried to eavesdrop, since any listening in would leave an unmistakable trace. It's a way of sending secrets whose safety is guaranteed not by clever math alone, but by the fundamental laws of nature. And the same exquisite sensitivity that makes quantum states so fragile also makes them wonderful sensors, able to detect the faintest whispers of magnetism, gravity, and time, finer than any ordinary instrument. So the next time someone tells you quantum physics is useless abstraction, you'll know better. It's in the screen you're looking at, and the chip that runs it. It's in the light that fills your home, and the beam that carries your voice across the world. It's in the scanner at the hospital, and the clock on the satellite guiding you home. The strangeness we've explored tonight is not far away at all. It's woven quietly into the ordinary fabric of your days, humming beneath the surface of nearly everything you use. The dream and the daily life turn out to be the very same thing. And so our slow journey through the quantum world comes gently to its end. We began with the simple glow of warm things, and we followed the thread down and down, into light that arrives in tiny packets, into particles that travel as clouds of possibility, into the soft and unavoidable blur at the heart of everything. We met the strangeness of being two things at once, of slipping through walls, of distant particles joined across the dark. We stood at the honest edge of human knowledge, where the finest minds still don't agree on what it all means. We found that empty space is quietly humming, that everything is ripples in invisible fields, that even living things may lean on quantum rules, and that this whole strange world is already at work in the ordinary tools of your daily life. If there's one gentle thought to carry with you into sleep, let it be this. The universe is far stranger than it first appears, and yet it is not chaos. Beneath the strangeness runs a deep and patient order, a set of quiet rules that hold the stars together and let leaves catch the light and keep the floor beneath your feet. We don't understand all of it, and perhaps we never fully will, and there's a real peace in that. Not everything has to be pinned down and made certain to be real or to be beautiful. Some of the truest things in the world are soft-edged, uncertain, and shimmering with possibility, right up until the moment we look. Thank you for spending this quiet time with me tonight. Thank you for your curiosity and for your company. However far you traveled with me before your thoughts began to drift, I hope it was a restful journey. Let the questions loosen their grip now. Let the ideas fade like a tide going out. You don't need to hold on to any of it. Rest easy, breathe slowly, and let yourself drift down, softly, into sleep. Good night.